So I'll share my, okay, fine for me. Can you see the big slide?
Yes. Perfect.
And also the pointer, right? Okay.
Yeah.
So thanks a lot for having me today. And it's a great pleasure to be at least virtually there with you in Baton Rouge, in Louisiana State University. It's a place I wanted to visit since a long time, but there's always been something in the middle. But anyway, so today, as I was telling you before, I will be telling something mostly conceptual, and it is related with the second law of thermodynamics. Why? Because in the past few years, I have been very interested in this new wave of papers, new wave of works, trying to bring a quantum formalization into thermodynamics. And in the process of, I had a few contributions in that direction, but in the process of writing those contributions, I realized that I was still kind of confused about the real meaning of the second law of thermodynamics. And this would, would cause troubles. I mean, if I wanted to understand what could have been a good quantum extension of the second law, first I would have to understand what is really at stake with the second law. So this work, which is in collaboration with Valerio Scarani mostly, and recently a student also, Valerio Scarani, Clive, joined in the project, is the fruit of, I would say, maybe a couple of years of intensive studies in the foundations of the second law and what's behind the second law. And this naturally led me to consider the literature in statistical mechanics, in particular, the literature about fluctuation theorems and fluctuation relations in statistical mechanics. So the idea would be that once we understood well the conceptual foundations there in classical fluctuation relations, then it would be easier to aim at the right target in quantum theory as a generalization of these things. Okay, let me start with a parable, let's say. So you probably have heard recently about this big anomaly with the muon mass measurement recorded at Fermilab. An anomaly that essentially causes troubles with the standard model. And everyone has received this news with great excitement. More than, even though the standard model is a very strong model that we have at hands, one could have, said that this result could have been raising some eyebrows, but instead it's been just accepted with a lot of excitement as pointing towards new physics. But if you see something similar to this, but in a different topic, like these things that I could find on the Daily Mail online, so it's a tabloid, of course, like this kind of news could have only been published on the Mail online, but there was something similar, like new physics, results that break like a previous physical theory, but this time the physical theory that is being broken is thermodynamics, and in particular, the second law of thermodynamics. So even though from the newslet viewpoint, these two news can look quite similar, actually we know this is not the case. The first one is pointing towards new physics, and it is been rightly accepted with excitement. This one instead seems just pure nonsense, right? So there is this kind of strange feeling that we have about the second law that makes it stand out from the other physical laws as something very special. And this is something that has been noticed before already. In particular, why? Because the second law is essentially the axiom that perpetuum mobile machines do not exist in the real world. And this is something that is deeply rooted in our in our understanding, we know that probably because we evolved in a rush environment, in a harsh environment, we know that lunches do not come for free. And so we do not believe that something as good as a perpetuum mobile machine will ever exist. And indeed, even before thermodynamics, it seems that people had the impression that these things would not exist, would look like kind of black magic, like the chimera. No, there is this quotation from Leonardo da Vinci, who lived 400 years before the formalization of thermodynamics, speaking against people looking after this perpetual motion, even though he actually worked on some kind of designs for a perpetual motion machine himself, but as is in this famous excerpt from his codes.
So Francesco, you showed this picture of cat bread. You have to tell us something about that. You can't just skip over that. Yes.
This is another proposal for a perpetual motion machine I found on the web, right? Yeah, so it is something that it is very deeply rooted in our minds, even before the formalization of the second law of thermodynamics. And the speciality, the special role of the second law was highlighted very nicely around 100 years ago by Sir Arthur Eddington, who wrote that the law of that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it to collapse in deepest humiliation. But also Albert Einstein wrote about this special role of thermodynamics and the second law, saying that these are the only physical theories of universal content concerning which I'm convinced that it will never be overthrown. And the second law is special amongst the laws of physics, but it is also very popular. Somehow it tickles some curiosities that we have about the world and the universe. And it is something that everyone should know, or at least this is the idea of Charles Snow, who wrote that essentially knowing the second law or asking about knowledge of the second law is akin to asking about knowledge of work of Shakespeare's for English-speaking people. So something that everyone should know. So what is the second law? What is the to be or not to be of thermodynamics? This is what we've said before. This is an axiom, first of all. We have to remember that the laws of thermodynamics are axioms. And essentially, the second law of thermodynamics is the axiom that a perpetual mobile machine of the second kind is impossible. And you can formalize this in various mathematical ways. And the most popular one is the idea that the total entropy increases. And then one has to be careful here because this is the total entropy, not just the local entropy. The fridges exist, right? So it is the total entropy change of system and environment, and not only. If you go deep into statistical formulations of thermodynamics, then you have to understand that this is an average variation. So you can have fluctuations, and you can have some what people call transient violations of the second law, but in average, the second law, this inequality must be obeyed according to the second axiom of thermodynamics. But again, why does the above inequality feel so special among physical laws? We cannot invoke the fact that perpetual motion machines do not exist, right? Because we would end up in a logical logical circle, right? It would be a circular argument, because this is exactly the second law is the axiom that perpetual motion machines of the second kind do not exist. So this is the question: why the second law is so special? Is entropy the key? So actually, now that we are stuck with COVID, probably if you are like me, you have been looking about things on YouTube, searching, looking for videos of people explaining stuff to you. And there are plenty of videos that explain the second law to the layman, or even not the layman, even people with a kind of scientific background. And it seems that they all end up in explaining what is entropy, as if the second law was about entropy. If you understand entropy, you understand the second law. So to understand entropy, of course, you have a lot of arguments. Essentially, you can always use discounting arguments. The problem is that no one understands entropy very well. This is, most probably not true that von Neumann said this to Shannon, but it is nice that somewhere it is still reported, because it fits very well in this talk. No one understands entropy very well. And anyway, that's only half of the story. So even if we understood entropy very well, and I think we can understand entropy very well from many viewpoints, still we would not understand why such a thing cannot decrease, or what is the meaning of the second law. And in fact, you can have a second law without entropy, or well, entropy is somehow hidden in the notion of free energy, but there is no entropy appearing explicitly in the following formulation. That is a formulation that takes just a piston with some gas. Typically, it's a gas made of few particles, so that you have this statistical fluctuation that becomes important and measurable. And it starts with this gas in thermal equilibrium with the surrounding environment. Then you isolate the piston, and you plunge the piston in with a certain force. And this will lead you to do work on the piston. And Clausius inequality here tells you that the average work that so you can repeat this process many times. And in average, the work that you put in plunging the piston inwards, it is lower bounded by the change in free energy of the Hamiltonian corresponding to the expanded piston, and the Hamiltonian corresponding to the compressed piston. This was a law that was formulated in 1865. It is one of the many avatars of the second law of thermodynamics. And it is most remarkable fact that we had to wait more than 130 years to discover, just by rewriting these terms using exponentials, you would be able to convert what is an inequality into an equality. This is the famous celebrated result by Jasinski, 1997, which essentially says that Clausius inequality can be turned into an equality if you take, instead of the average of the work, you take the average of the exponentiated work. And this turns to be equal to the exponential of the free energy difference. So Jasinski equality points to the fact that if we want to understand what's behind the second law, we have to go into a statistical formulation of thermodynamics, where things now are not just functions of process and states, but are random variables themselves. Work becomes a random variable with a distribution, with a probability density, if you imagine that work is a continuous thing. And it tells you that however your work is distributed, just by taking, from Jasinski equality, you can just apply Jensen inequality and derive Clausius inequality as a consequence. So it would tell you that essentially the average of the work, which can be roughly here, let's say, is going to be lower bounded by the change in free energy that will be somewhere around here. It will be on the left of the average work done. So Jasinski implies Clausius, but we can go even deeper. We can find something that implies Jasinski. And this is related with the idea of irreversibility. So now, to derive this other result, we have to consider not only the forward process of plunging the piston inwards, but also the reverse process of pulling the piston outwards from the piston. And the idea is that in the forward process, you start, as I said, with the gas in thermal equilibrium here, and you push it, you compress it. And in the reverse process, you start with a compressed piston, but the gas again is in thermal equilibrium. This is the point. And now you pull out the piston from this position. A theorem by Crookes, formulated just 2 years after Jasinski equality, tells us now a very beautiful relation between the work distribution for the forward process and the work distribution for the reverse process. And their ratio should satisfy this equality here. And it is possible. So now we have two curves, a distribution for the work for the forward process, a distribution of work for the reverse process. And we see that they will cross somewhere, wherever they cross anyway, they will cross exactly at the energy difference point. And then it is possible to show that Crookes theorem implies Jasinski equation that in turn implies Clausius inequality. So if we keep this as a kind of prototypical formulation of the second law, we would like to understand what are the assumptions that permit the derivation of Crookes fluctuation theorem. And these are the following. So these are two assumptions that are satisfied at equilibrium. The first assumption is that at equilibrium, the microstate probability is given by the Gibbs distribution. So the probability of finding the system in microstate psi is proportional to the e to the minus beta. Beta is the inverse temperature times the energy of microstate psi. And the second assumption is the assumption of microscopic reversibility, which should be compared, is closely related with the assumption of detailed balance. Sometimes people invoke detailed balance, sometimes they invoke macroscopic reversibility. There are two slightly different concepts, but still very closely related, and they both essentially express the fact that molecular processes and their reverses occur at the same rate when we are in equilibrium. So in equilibrium, you have various molecular processes that transforms things into each other, transform states, but if macroscopic reversibility or detailed balance are satisfied, then molecular processes and their reverse processes occur at the same rate. So that essentially, if by looking at the system from far away, you will see no change in its state. But again, I'm not happy. I still do not understand why the second law feels so special. In particular, I'm not happy at all with the idea that the second law seems special because of some special microscopic balancing mechanism. I don't want to think about thermodynamics as something that happens at the level of microscopic Hamiltonians, right? In this sense, I'm very much sympathetic with Edwin James' way of thinking about thermodynamics, where he writes that to understand and like thermo, we need to see it not as an example of the n-body equations of motion, but as an example of the logic of scientific inference. So I would like to see the second law as emerging from inference, from the logic of inference, rather than from some microscopic balancing mechanisms. Can this be done? So the first idea that we had was to see the reverse process as Bayesian retrodiction now, not as an actual process that happens in reverse, but as just like a form of inference backwards in time. Let me try to clarify this point a little bit further. So when we speak about Bayesian inference, we have to introduce Bayes' Laplace rule. And Bayes' Laplace rule is formulated in this way, where you have a prior, you have a conditional, something that looks like a conditional probability of data given hypothesis, which is interpreted as the likelihood or as the statistical model that you are applying in order to explain the data that you see. And Bayes' Laplace rule is a rule that tells you how you should update your prior distribution on the hypothesis given the data D. So a lot have been said about Bayes' Laplace rule. In the past century, in the 20th century, actually saw the two camps of orthodox statistics, the statistics of Fisher, the statistics of that we call nowadays the frequentistic approach to mathematical statistics, against the Bayesian camp. And it was a a bloody war between these two camps. Fortunately, nowadays we can say that we live in a postmodern world where ideologies are left behind. And so we are free to use ideas without subscribing to any ideology behind them. And this is what will be done in this talk. So we will be using just Bayes' rule as a tool to define inference, and in particular prediction and retrodiction. So don't be upset by the appearance of a prior here. It's a tool. It's something that we need in order to introduce retrodiction. I am personally speaking a Bayesian, a convinced Bayesian, but I wouldn't be willing to go into such a debate today. So what is the inverse probability? So inverse probability is the main tool of Bayesian statistics for problems like estimation. For example, how many red balls are in an urn, or decision. So is Acme's stock a good investment, or should I buy some? How much? How to allocate your portfolio of stock options, for example. But also in inference and learning. For example, predictive inference, weather forecasts, they use a lot Bayes' rule in order to learn the weather of tomorrow's weather given the previous records of weather and the present, for example, radar map of the clouds around your country. But also for retrodictive inference. Retrodictive inference is something that is not as natural to us as predictive inference, but it is a perfectly solid branch of statistical inference, and there are entire scientific endeavors that are entirely based on retrodiction. For example, cosmology and astrophysics are entirely based on retrodiction. Not only because what we see from the skies is a snapshot of something that happened millions and millions of years ago, because light takes time to reach us, but also because we cannot prepare two cosmological objects and make them interact as we do with particles. So we do not have control on initial conditions of things that happen in the cosmos, but we can only look at the events and try to retrodict what was behind it. For example, what was the stellar event that possibly caused the Crab Nebula to appear in the sky? And if people instead have also a Bayesian understanding of probability, then inverse probability gets a richer and deeper meaning as the degree of belief that the rational agent should have in one hypothesis, among other mutually exclusive ones, given the data. But there is one point that it is often ignored in textbooks when the Bayes-Laplace rule is introduced. And the point is that Bayes-Laplace rule tells you what to do with data, but doesn't tell you what to do with your data are noisy, or when your evidence is uncertain, which is actually most of the times in actual scenarios, right? Suppose, for example, that I have a problem that requires an inferential problem that requires as data the license plate number of this car. I shoot a picture, but the picture is so noisy that I can only kind of guess what is the license plate number here. Maybe I can say that the first thing here is an A and then a Y, something like that looks like. But I would be a fool to ascribe to the data A and Y 100% confidence, right? I can only say kind of that the probability that this is an A is this much, but there could be some non-null probability that is not an A actually. So we should be able to deal with data that are presented to us by a probability distribution Q over the data. So it's not that we are observing some well-defined data, say D bar, and we use that in the Bayes-Laplace rule formula to derive the inverse probability, but we are given a probability distribution. And in this case, Bayes-Laplace rule does not tell us what to do with this probability distribution. This must be very clear. So what do? We have to extend Bayes' Laplace rule in order to deal with uncertain data. And this extension is what people call in the literature about the foundations of probability theory, Jeffrey's rule of probability kinematics. So on one side, we have vanilla Bayes, that is the usual Bayes formula that can be applied when D is something specific that you've seen with full confidence, 100%, you've seen D and nothing else. Whereas instead, when you have a probability distribution over the data, you need Jeffrey's conditioning rule that can actually be derived as a result of Peirce's method of virtual evidence and Bayesian networks. But in some situations, it just have to be postulated, okay? But this would bring us in a completely different direction. Just say what Jeffrey's conditioning tells you. It tells you that you can use the inverse probability now, not as a probability, but as a noisy channel to back propagate your uncertain evidence on the data onto the hypothesis. And this inverse probability is the inverse probability of Bayes' Laplace rule. So Jeffrey's rule of probability kinematics that can be derived as a theorem tells you that actually that inverse probability can be seen as a channel that backpropagates uncertainty from data onto the hypothesis. But one should understand that Bayes' Laplace rule on its own does not grant you that freedom. Okay, even though it looks like a conditional probability, it is not a conditional probability. It is an updated prior in vanilla Bayes. So we need Jeffrey's condition. So now that we have all the tools that we need to do retrodiction, Bayesian retrodiction, also in the presence of uncertain evidence, we can start to construct the physical setup that will lead us to fluctuation relations for Bayesian inference. So the physical setup is by giving a stochastic transition rule that tells you the probability that your system will jump in macrostate Y, given that the initial macrostate was X. We can imagine that this is all what physics tells you. Physics basically set up the stage. And then what happens on the stage, it is just inference, a predictive inference, if it is inference about what will happen after you prepared your system, or a retrodictive inference that can tell you what happened before, after you observed some, or after you are given some noisy data about your system. Given the stochastic transition rule phi, then you can compute a steady state, an invariant distribution from it. You know that at least one will exist for sure. And then you construct Bayesian inversion at the steady state. Why you do that? Because at the steady state, it is, we are interested in fluctuations around equilibrium. Equilibrium corresponds to a steady state. It's a state in which things do not evolve. So it is sensible to construct your framework around the steady state. And we will be constructing the Bayesian inversion at the steady state, but you need not do that, okay? So the formalism of retrodiction allows you to do retrodiction also to retrodict about something that is not the steady state. It is just that if you want to reconstruct known fluctuation theorems, you have to start from equilibrium. So you do this inversion here and you construct this phi hat. And now you imagine two agents. You imagine a predictor that will start with some knowledge about the state of the system at some time t0, given by this prior px. The prior px need not coincide with the equilibrium distribution. It's just another prior that the predictor will use to predict the macrostate distribution in the future. And then you can also give a retrodicting agent, a retrodictor, some prior qy about the macrostate of the system at some later time t1, and the retrodictor will use phi hat to retrodict the corresponding distribution over microstates of the system at time t0. So you have two processes. You have a forward process, which is the prediction, and you have a reverse process, which is the retrodiction. Now, given these two processes, forward process, which in our understanding is not an actual process, physical process, but it is just a forward prediction, a forward inference, and a reverse inference. Okay, there is a picture first. Sorry, I forgot about this slide. So just to give you a picture, you can imagine that you have now two boxes. You have the forward process box, and you have the box reversed at the steady state. So if you plug the steady distribution in these two boxes, the predictor and the retrodictor will agree. So you will end up with the same joint distribution. But if you plug things that are different from the steady distribution, the predictor and the retrodictor will disagree. So you will end up in a state of asymmetry between predictor and retrodictor, or if you want to call it like irreversibility, but even better, I would call it irretrodictability. I wouldn't like to call it irreversibility because then, you know, there is this paradox, how irreversibility emerges from a reversible mechanism underlying it, no? Like classical mechanics is Hamiltonian, quantum mechanics is also Hamiltonian, is reversible. And so people say, oh, how you get irreversibility from a reversible theory? It is just because here it's a completely different sort of irreversibility. It's irreversibility of this stochastic model, which is already something completely new, okay? So there is no paradox. That's why I prefer to call it irretrodictability, to demarcate, to clarify the difference between the mechanical reversibility and inferential irretrodictability. But okay. So now that we have two different, a predictor and a retrodictor that do not agree, we want to quantify their difference. So in order to do that, we use divergence, stochastic divergences. For example, we could use the relative entropy defined in this way. Okay, so the relative entropy between the forward process and this reverse process, which is defined in this way, and crucial in determining the divergence is the ratio between these two things. It is so fundamental that the ratio appears as the core quantity, not only for relative entropy, but also more generally for F divergences. F divergences are essentially averages of functions of this ratio, right? Now, Mark will tell me that, oh, but F divergence, what you've done before is not the relative entropy, but it is the inverse entropy. Yes, we didn't use x log x to derive relative entropy, but just minus log, because it is easier than to derive other formulas. But we didn't do the calculations for all F divergences, but for a good chunk of them, maybe it is, you know, also an interesting direction to follow. Really like to have these F divergences.
I think what you're doing is fine. I don't have any problem.
Okay.
But
Yeah.
I mean, like negative log is a convex function, and then it's an F divergence, right?
Yes. Yes. But typically, you know, in mathematical statistics textbooks, relative entropy is the thing that is defined from x log x averaging on the second one, and minus log is so-called reverse entropy.
Yeah.
But that's fine, I think. No, we can say that this is okay.
All right.
And then from here, you can actually say, okay, the ratio is so important that now this will be my fluctuating variable. Actually, this is what you do to derive fluctuation theorems. Fluctuations, what is fluctuating is this ratio, or better said, the function of the ratio. So you say you introduce this random variable that depends on the microstate of the system at initial time x and final time y as a function of the ratio. And sometimes it's called the total stochastic F entropy production. And then you can just formally introduce some probability density for these things just by using the trick of having the Kronecker delta function here. And then you will see that the average of this fluctuating variable omega is the F divergence between reverse process and forward process. But let's say that this is a kind of
All right, I have a technical question. Can you go back to the previous slide? So mu f is a probability density function. Is that right?
Yes,
Okay, and the same for mu r.
mu r, yes.
Okay,
Yes.
and then
This
the
is what
last
people,
one, you're calculating, oh, the average with respect to mu f. Is that right?
exactly, that's
Okay.
exactly the
Right.
case.
All right.
And this is just a trick, because then because of this delta function, you will have that this is just the average of this big omega done with respect to the forward probability distribution. But
Okay.
anyway, because people like to imagine work as a continuous variable, they like to introduce these probability density functions in this way.
All right, and you're going to tell us a bit like why, now you're going to tell us why you're doing that. Okay.
Yes, and well, just this tells you that if you like, you know, to see things from a little bit above, if you are happy with divorcing for a while from this thermal narrative that people usually use in when introducing fluctuation relations, and just by looking at these things from the statistical viewpoint, and you can have very easily F fluctuation theorems. You can derive a Crookes theorem and a Jasinski-like equality for a lot of these F divergences here. But this is not the core of the message now of this talk. This is a kind of side product that tells you that sometimes divorcing from thermal narrative can be good. You know, it can lead you to a wider perspective on the problem. But I would like to go back to the second law, because that is the main point of this talk. And I would like to show you how some known results about, fluctuation relations are recovered by retrodiction. So take the simplest example of a driven closed system evolution. So where you have a system with which you can only exchange work. So you have the Hamiltonian of the system that is brought from h0 to some h tau. There are some parameters that you can control of this Hamiltonian, and the evolution is still Hamiltonian. It is still one-to-one. It is fully deterministic evolution. And so this phi, that was the stochastic matrix that would regulate the transitions between microstates, is a delta, is a one-to-one function, right? A delta between y and y of x, because now y is a function, deterministic function of x. So for example, an invariant distribution is the uniform one. And so this leads you to conclude that phi is equal to phi hat of x given y. And so in particular, you can say that it satisfies, it satisfies this relation. So this makes things a lot easier. And now you can give the predictor the thermal distribution. You can give the retrodictor the thermal distribution at the end for the final Hamiltonian. And just by applying the formulas blindly, so just by introducing this omega here as the logarithm of this ratio, and now you will see that this ratio simplifies a lot because of this condition here. Sorry, because of this condition here between phi and phi hat. This ratio essentially becomes just a ratio of the equilibrium distribution. Equilibrium is always kind of thermal equilibrium. Here is not thermal. This is invariant distribution S. And these prior P and Q, which are the one at thermal equilibrium, but are not invariant, right? Because this is not a thermal preserving process. So this goes away because this is just d to the -1, and you're left with this log of these two ratio of two Gibbs distribution, and this leads you to this equation. So it's a change in energy and a change in free energy, and because the energy change can only be explained as exchange of work, because your system is otherwise isolated from the thermal environment, then you can say that this is entirely work. So you see that you do not need to introduce a time reverse process by using time reversal maps between Hamiltonians and introducing a reverse Hamiltonians with reverse momentum. Same, you reverse the momenta. You keep positions the same. You have to invert a magnetic field if one is present. You don't need to use all this, like, it is just a recipe that people use, but I wouldn't understand exactly why it works. It is just work because it is how you get retrodiction. That is the only reason why time reversal is defined in that way, because it gives you Bayesian retrodiction. You can also have a little bit more complicated scenario, like a non-equilibrium steady state. This is a topic that is extremely important in statistical mechanics. So now imagine that you have a stochastic process whose invariant distribution is not a thermal steady state. So now you start again with priors that are at thermal equilibrium. And again, you compute the fluctuation variable here. So now this object here will not go away in general. You still have an Sy divided by Sx. So you end up with a fluctuating variable, which is a beta energy difference plus this difference of these logarithms. So the interesting thing is that this logarithm of Sy and Sx were introduced ad hoc in previous literature. You can have a look, for example, at this paper by Manzano, Horowitz, and Parrondo in 2015, where they call these numbers non-equilibrium potentials. And they were introduced in order to have the formulas consistent, in order to derive a Jasinski equality in more general situations where instead people would have something that is not one, but it is what people call efficacy. If you want it to be one, you had to introduce this non-equilibrium potential as ad hoc correction to your equation. But here we understand non-equilibrium potential as just remnants of Bayesian inversion. So again, you need not start from Hamiltonian, apply the recipe to cook up the time reverse Hamiltonian, and then add non-equilibrium potential in order to have things sum up to one. You can just start from Bayes' rule, and then everything will come to you extremely naturally. Okay. So, but why known relations are compatible with Bayesian inversion? Is that a necessity, or it is just a coincidence that what we know is just happen to be compatible with Bayesian inversion? No, to a certain degree, it is actually a necessity. And I will show you why with this sketch argument. So we start from this ratio again. You have the fluctuating variable, which is the function of the ratio. And then you take the average of the fluctuating variable. So now let us impose that this fluctuating variable, which is sometimes called the, as I said before, the total stochastic entropy production, or more precisely in some papers, this is called the non-adiabatic stochastic entropy production. But anyway, this is the thing that people care about in statistical mechanics. So let us impose that this thing, that is the thing fluctuating, is local. In the sense, it has nothing to do with non-locality, entanglement, Bell non-locality. It is local in the sense that it can be expressed as a difference of two functions that can in general be different, g prime and g, but are evaluated only on x and on y. So this is not a function that depends on the stochastic matrix that brought you from x to y, but it is just a difference that depends of two functions that depends individually only on y and only on x. And this is what happens, by the way, for entropy production, right?
Just to clarify, G prime is not the derivative, or it is the derivative?
What is equilibrium? No, in general.
No, sorry, G prime, just some notation question. Does that mean derivative or different function?
Oh, no, sorry. No, it has nothing to do with derivative. Just another G.
Just another function. All right, thank you.
Just another G prime. So if you take the logarithm of this thing and noticing that PF and PR as some already they factorize because of the product rule of a joint probability distribution, you end up finding out that the ratio between the two transition matrices must be equal to the ratio of two functions, some H prime and some H. of y and x. So this tells you that because these are positive, we can assume that these are all positive numbers, right? This tells you that this h prime and h will always have the same sign. Either they're all negative or they're all positive, because their ratio must always be positive, right? So say that you take them to be positive. So now you can just redistribute this hx on the left and keeping h prime y on the right. And so you sum over x. And because this thing here is a normalized conditional probability distribution, you end up finding that this h prime y is just, hx propagated through this noisy channel PF. So basically, you end up with a Bayesian formulation of these things. Whatever is this h from which you computed g by taking the logarithm, the relation between the reverse process and the forward process looks like Bayesian inversion. So as long as you want your fluctuating variable to assume this local form, you are forced somehow to find out that your reverse process was obtained with some kind of Bayesian inversion from the forward one. So let me say it once more. A Bayesian inverse-like form for the reverse process is inevitable if we want a fluctuating variable to have a local form. And this to me is it is something that clarified my understanding a lot. Well, finally, so what about the quantum case? So
I'm sorry, may I interrupt, by the way?
Oh, yes, of course.
Okay, I want to understand, you might have said it already, but I want to understand better, why are you looking for the fluctuation variable specifically in the local form? Like, what's the purpose behind it? Can you repeat it exactly?
Well, in a sense, it is natural. Well, it is an assumption that people might say, okay, I want a fluctuating variable that is not local, perfectly fine. In that case, you can have a reverse process that is completely general. There is no relation between the reverse process and the forward process. But a reason to have a fluctuating variable in local form, well, first of all, entropy satisfies that, right? Like if we go back to all previous fluctuation relations, the thing that was fluctuating was a difference of energies, for example. The energy for the final state minus the energy for the initial state. Or maybe there were some correction terms of this non-equilibrium potential, but also they were expressed, as you see here, as a difference of things computed at y and things computed at x. Notice, however, that just by assuming that the fluctuating variable can be expressed in this way does not tell you that when you take the average, you have a state function, right? Because you're still averaging over something PF, which is not in product form.
Right, exactly, yeah.
So this is something that really goes at the bottom. Like I'm just saying, it is a very, very weak assumption. It is just telling you that the fluctuating variable is expressed in this local form. Mm-hmm. At present, I have no good reason to tell you why this is the only thing you would like to do, why other fluctuating variables would not be as meaningful as local fluctuating variables. I'm thinking about it. I think this is an important point, a very good question. But for the time being, you can just take it as an assumption. If you want your fluctuating variable to be of this form, you're somehow forced onto a Bayesian sort of retrodiction, yes. reversal.
I see. Yeah, thanks for the clarification, Francesco.
Thank you for the question. It was a very good point. Finally, what about the quantum case? So this seminar series is about, I think, QST, probably quantum science and technology seminar series. So there was no quantum in my talk until now. So let me repair my my talk at the very final slide, just by showing you that essentially Pet's recovery map is a quantum Jeffrey rule. It's nothing but that. And actually, it seems that in the quantum case, you really don't have a proper Bayes. Bayes rule, vanilla Bayes rule is not there so much, or where there were people that were arguing that you don't have a proper Bayes rule for quantum theory, but you can have a proper Jeffreys rule for quantum theory. Well, here I will just focus on the so-called two-measurement formulation of quantum thermodynamics, which is a kind of semi-classical formulation of quantum thermodynamics, because still you see that the input here is a classical label X, and the output is again a classical label Y, but you just imagine that the classical label X gets encoded on some states, rho X. Then the states go through some quantum process E, which is modeled by some CPTP linear map. And then the output is measured with a POVM PY, so that at the end you still have a classical transition matrix, but the transition matrix that has a kind of quantum mechanism behind. So now let Sx be the invariant distribution for this classical transition matrix here. And then you just apply the formalism of quantum retrodiction that was there already before, and people didn't notice the connection with Jeffreys' rule, but was there somehow in bits and pieces, dating back from to work by Barnett about quantum retrodiction, and then this was taken up again by Chris Fuchs in early 2000, and then there is work by Leifer and Speckens, 2012, 2013, where again they revisit these ideas of quantum retrodiction, but the formulas are very straightforward. So somehow Petz's recovery map is forced upon you if you want to be consistent here. So you just introduce a state big sigma here, and then you just use this big sigma to define states rho hat Y, which are constructed starting from the POVM element at the end of the process. And then you have POVM elements P hat X, which are constructed from the states rho X. So states become POVMs elements, the POVM elements become states. So you are flipping somehow the time order of the circuit, but it is not anything that you're doing actually. This is just retrodiction, something that happens in your head. And then also the channel gets inverted or reverted according to Petz's recipe, right? So Bayesian inversion works seamlessly in this way. So if you apply this recipe that I gave you on top and you compute the corresponding transition matrix that you get, this is exactly what you would get from phi by applying Jeffreys' rule.
That's very interesting. I have a question.
Yes.
Why are I was trying to figure out while you were talking why the rho hat Y's are states. Is that obvious? So I mean, it's obvious they're positive semi-definite, but why is the trace one? Is that simple to see?
Yes, this rho Y, they are all trace one.
Mm-hmm.
And this pi x, they sum up to identity.
Yeah.
So this is
the question is, why is the rho hat Y trace one? Is it obvious, or is it, do we have to like go to a blackboard and write like 10 lines to see it?
I mean, the calculation that this trace is one.
Mm-hmm.
Yeah, like, so you take from the definition of E, you apply E to this big state here, this sigma here on top, and then you just carry out really like straightforward algebra.
All right, I'll try that.
It's really straightforward. And it could be, you know, it could be, but you notice this in your own textbook. It could be that E hat is not CPTP everywhere, but only on a subset of operators, but you can extend without any trouble this to a CPTP linear map everywhere.
Yeah.
So it's something that is, it doesn't pose any formal problem here.
That's very nice, that last formula. Very beautiful.
This
That's in
one,
your
you mean?
That's in your paper, or that was discovered earlier? Or?
I wouldn't call it a discovery. It is really just by applying the idea of retrodiction to these two measurement quantum formalism for fluctuation relations. And you will see that Petz recovery maps just lead you to the reverse stochastic matrix here.
Yeah.
Just things, you know, they get together nicely because there is no choice for them but to get together nicely, because we're speaking about consistent inference here. So if something doesn't match, it means that there is some big problem there, that at some point the inference chain got astray and you are not reasoning in a consistent way. So we expect that formula gets well together. Actually, I would expect that also the fully quantum fluctuation relations follow from a retrodictive argument. There you wouldn't have a classical input and a classical output, but you would really have a fully quantum fluctuation relations. And people had been using Petz recovery map there just because it worked, just because it led them to have something that looks like a Jarzynski equality. But here we would understand why you need Petz reverse map, because that is how you do consistent retrodiction. This is how you consistently construct a reverse process in the quantum case as well. So the next step is to prove that quantum retrodiction also provides the logical foundations for fully quantum fluctuation relations. Thank you for the question. So just some remarks about quantum retrodiction and Petz recovery map. So Petz recovery map reduces to Basel plus rule, or even better, to Jeffrey's probability kinematic rule when operators commute. And to a unique Basel plus rule, I say unique because Basel plus rule has been derived as the inevitable form of inference according to a lot of criteria. But again, you are very free to do something that is not Basel plus, right? You are free to do inference using a formula. For example, I think that Google, they use some kind of weighted Basel plus rule to update their page rank numbers. But if you want to be consistent, if you want to be to escape from a Dutch book attack, sort of an attack, then you have to follow Basel plus rule, which is unique in the classical formalism, but there are infinite possible Petz maps, so-called rotated or swiveled Petz maps in the quantum case. So this is very interesting because it tells you somehow that in the quantum scenario, you might have more than one possibility for you to retrodict. It is not just a matter of forward and backward, but you have many backward processes that all become Basel plus rule in the classical case. Then retrodiction, as a matter of fact, there is nothing we can do about it. Depends on the choice of a reference prior. If you don't like a prior, you should put a uniform prior, or if you really don't want to do prior, then you cannot do retrodiction. You know, retrodiction is inherently a Bayesian concept. Exceptions to what I said before are unitary channels, or to use a nomenclature used by Satoshi Watanabe in the 50s, who wrote a pioneering paper, I would say, called Prediction and Retrodiction in Quantum Theory. He calls them bilateral or bilaterally deterministic channels because they are deterministic channels in both ways. So for unitary channels, there is a unique Petz reverse. The retrodiction is independent of the choice of prior, and all rotated Petz maps coincide because the invariant state is the identity. So it commutes with everything. So when you take identity, you know, the complex exponential of the invariant state is just identity. And retrodiction and linear inversion coincide. So this is another big point that people have been making, myself as well at the beginning. I was confusing a lot between retrodiction and linear inversion. These are two completely different things, two completely different ballparks. If I am at a receiving side of a channel, I don't do linear inversion of the channel to decide what was the input. I will do statistic retrodiction, or I will use some kind of statistic inference to try to infer the letter that was input to the channel, right? So retrodiction and linear inversion are in general completely different things, but they coincide for unitary channels. Conclusions. So I already been speaking for too long. I'm very sorry for that. So final messages. Predictive and retrodictive inference provide the logical foundations of fluctuation theorems, or at least this is what we believe. While fluctuation relations measure the divergence between the predictor and the retrodictor, the second law states that their disagreement won't increase as a result of their inference. So the more the predictor and retrodictor infer, the more they go ahead in the logical chain of inference, the more they will tend to agree. They will not disagreeing more than what they were disagreeing before. This is another way to look about equilibration processes for systems. The systems will go towards an equilibrium state, or put in the language of inference, you can say that predictor and retrodictor will tend to agree in the future as time passes. So now we understand that the second law is special among the laws of physics because it is in fact a law about logic of inference. It is not so much about physics as it is about logical inference. So if you violate the second law, it seems that you're violating some basic principles about logical inference. And perpetuum mobile machines won't work because those would be just a kind of mechanical retrodictions, right? So a mechanical retrodiction can be as not better, of course, than full logical retrodiction. It would be kind of approximation of logical retrodiction. And if there is asymmetry for logical retrodiction, that must be asymmetry for mechanical retrodiction. And that's why perpetual motion machines won't exist, right? Because they would just give you a way to retrodict, or they would make prediction and retrodiction symmetric. And then we have a clear distinction between mechanical irreversibility and logical irretrodictability. And this avoids unnecessary paradoxes. Like Loschmidt paradox is really unnecessary. It comes from someone who did not understand what Boltzmann was speaking about. I understand Boltzmann's frustration somehow. Quantum retrodiction, and then finally, the final conclusion is that quantum retrodiction and quantum fluctuation relations follow seamlessly using Pet's recovery map, or at least this is what we found up to the two-point formalism of quantum thermodynamics, and we are working now on deriving fully quantum fluctuation relations as well. And I thank you very much for your attention. That was all.
All right. Thanks for your seminar. I have a number of questions, but are there questions from others?
I found your